So, by the way, before I forget to tell you guys, there are also some good examples of Jordan form calculations in the notes, like the double differentiation operator, example. Sorry, I'll tell you in a second here. Where is that stupid thing? Ah, curses. Where'd it go? Example 8.2.15 on page 222 is definitely worth looking at, guys. But now I'm going to turn the page here and sort of leave the problem of Jordan forms behind us for just a bit, and we need to talk about the so-called complexification, the complexification of a vector space. So what complexification is a technique to take any real vector space and form a corresponding complex vector space. In particular, if I have a real vector space V, I can form the complexification of V, which I call V sub C, by taking pairs of vectors. So really what I do is I look at V cross V as a Cartesian product. I mean, it's fine as a set. As a set, this is really V cross V, right? And I say that we can view, in fact, as a complex vector space, and here's how. First of all, addition on V cross V, well, that's the same as usual. We just add component-wise. But then here's the surprising thing. We can define scalar multiplication on V cross V, complex scalar multiplication on V cross V as follows. We do A plus IB times x comma y is AX minus BY, comma AX, AY plus BX. Now, of course, this is well defined because this is a linear combination of vectors, and that's a linear combination of vectors, so it's definitely in V again. And you can verify that, in fact, this definition for scalar multiplication of a complex number does satisfy the needed axioms for a complex vector space. In particular, you can show that 0, 0 is the 0 in the complexification, and if we look at 1 times xy, we get xy again. Let's see here, 1 is what? 1 puts what? Let me write it in here. If we just look at this for a second here. 1 is equal to 1 plus I times 0, right? So in other words, A is equal to 1, B is equal to 0. If you look at the formula right here, A being 1 puts x, B being 1 puts, B being 0 puts 0, A being 1 puts y, so we get x comma y. 1 times xy is xy. That's one of the things we need for the scalar multiplication to make sense. And then the other thing is, what does I look like? Well, excuse me. 1 plus 0 times 0. 1 plus 0i times xy. Oh, well, I just showed you that. Sorry, I'm an idiot. 0 plus I times xy is actually minus y comma x. So this is really a drag, this current notation. So we prefer to instead write x comma y as x plus iy. Here x and y are vectors. So if we use this notation x comma y as x plus iy instead, then we have 1 times x plus iy is x plus iy, and we have I times x plus iy is ix minus y. Because again, this in our newfound notation, this is minus y plus ix, right? So that's what we have right there. In other words, the complexification is effectively just looking at vectors of the form x plus iy, where you just multiply like you'd expect. So generally a plus ib times x plus iy is a times x minus b times y, so it's like I squared is minus 1, and we have I times ax plus by. So in short, this construction I've just shown you is a formalization which justifies this calculation down here. All right. So this again is the so-called complexification of a real vector space. And you can identify the vector space and I times the vector space as being subsets of V sub C. See, the vector space itself is vectors of the form x plus I times the 0 vector. I times V would be vectors of the form 0 plus ix. So the sum of v and iv is all the complexification. The intersection of v and iv is just the zero vector again. You can prove that. So we have that the complex vector, the complexification of v is in fact the direct sum of v and I times v in this way. But anyway, if I didn't have all this time to talk to you, and I wanted to get to the just the simple explanation for what the complexification is, I would just tell you this: the complexification of a real vector space VR is simply VC. In other words, what we do is we replace the real scalars with complex scalars, and that's pretty much all there is to it. But again, that's just a slogan for the formalization I just worked out for you guys. My phone is misbehaving. All right. So here we go, the definition. My daughter is talking for some reason. Let's see here. So V is a vector space. We define the complexification to be the complex vector space of the form x plus I, y, or x and y are in V. And we define addition like so. We define complex scalar multiplication like so. The real part of this is this. The imaginary part is y. And justification for this definition was just given on the last page. So here's some simple examples of complexification. If we have the reals, the complexification of the reals is the complex numbers. In fact, the whole complexification procedure I just showed to you is nothing more than the construction Gauss gave to just justify the existence of complex numbers on the basis of the real numbers. And all I've done is rip off his construction for an arbitrary vector space, real vector space. If we look at the complexification of Rn, we get Cn. The complexification of n by n real matrices, n by n complex matrices. All right. Furthermore, if we have a basis, a real basis for vector space, then you know what? That same basis also serves as a basis for the complexification of the vector space. And the proof is given here. I'll let you read it. It basically, well, anyway, I'll let you read it. I think I'm going to go on. So here's yet another example. Come on. Turning pages is a real chore for me today. So also, if we were looking at the complexification of polynomials with real coefficients, we get corresponding polynomials with complex coefficients. So let's see here. The thing that was a little bit sneaky about the theorem I just glossed over, I should probably say a word about this, is this I'm saying is a real basis. I'm talking about a basis for VC, which is a complex vector space. So I'm saying it's a complex basis in that sense. As a real vector space, VC is actually twice the dimension of V. Okay, but anyway, we'll get into that shortly. Like right here, P2 has basis 1t t squared. The complexification of P2 has real basis 1i t t squared it squared. But as a complex, if you were to think about the complexification here, W's this guy as a complex vector space, you could point out that the complex span of 1t and t squared does quite nicely. In other words, the complexification is 3 complex dimensional, but it's 6 real dimensional here. All right. Let's see here. If we have linear transformations from a vector space U to a vector space W, then we can talk about the complexification of V, just like we have already. And if T is in the complexification, then that means that T is L1 plus LL2, where L1 and L2 are in V, which means that L1 and L2 are separately just real transformations from U to W. And furthermore, if beta is a basis for U, then beta is still a complex basis for the complexification of u. And so T extends uniquely to a complex linear map, T sub c, from this to that. Therefore, we find that the complexification of V is, in fact, it's the complex linear maps from the complexification of U to the complexification of W. Oh, so much, guys. I'm sorry. I don't think we need quite all this. This we do need, so let's get to that. This is the main point. If we have a linear transformation that goes from a real vector space to a real vector space, then we can define the complexification of that map by T sub c from the complexification of V to the complexification of V, where of course the complexification is V plus IV again. And it's simply defined by basically enforcing linearity. I mean, so we say T sub c of x plus iy, it's T of x plus I T of y. So T is given, so T of x and T of y are given. And so what I'm defining here is the T sub c. In fact, I do this all the time in differential equations without even explaining any of this. I just, all of a sudden we're solving a real differential equation, and then I'll be solving a complex differential equation, and I just say, well, we make the differential equation complex. And so what I'm describing right now, the algebra of, is how you actually do that. Here's a typical differential equation example in that sense. To solve ay prime prime plus by prime plus cy equal to 0, we try to use the real solution e to the lambda t. Since lambda prime, y prime is lambda e to lambda t, and y prime prime is lambda squared e to lambda t, you plug these in, right? You make a guess, you plug it in, and because e to the lambda t is non-zero, this requires that the auxiliary equation a lambda squared plus b lambda plus c be 0. All right, so, but a, b, and c are real numbers, and so it doesn't have to be a real solution, right? It could have real solutions, but it might not, right? So if it does have real solutions, you're done. For example, this one gets real solutions, lambda equals -1, lambda equals -2, and that gives us general solution c1 e to the minus t plus c2 e to the minus 2t. But what happens? It's not always the case that we get real solutions to the auxiliary equation, right? We could have y prime prime plus y equal to 0. That would give us auxiliary equation lambda squared plus 1. All right, well that's got no real solutions. So what we do is we take this given problem, we complexify it. We study z prime prime plus z equal to 0, where z is x plus iy, and x and y are real valued functions of t. So the really cool thing is if we have if we have lambda is alpha plus I beta complex, then e to the lambda t by Euler's formula is e to the alpha t cosine beta t plus I sine beta t. And it's still the case, you can prove that z prime is lambda e to lambda t, and z prime prime is still lambda squared e to lambda t. Even though lambda is complex, the things you learn in Calculus 1 are still true for lambda complex, which is pretty awesome. So you still have the auxiliary equation, and so we get lambdas plus or minus I, and in the complexified solution we get z equals e to the it. That's a complex solution to the complexified problem. But fortunately for us, there is a connection between the complex differential equation that we were talking, the real differential equation, and the complex differential equation that we just solved. So we have e to the it and e to the minus it as complex solutions to z prime prime plus z equal to 0. And the neat thing is, if you look at z equals to x plus iy, you differentiate it and double differentiate it, and then you look at what it means, z prime prime plus z equal to 0. Well, that gives us that this is 0. So the only way you can have that x prime prime plus iy prime prime plus x plus iy be 0 is if separately the real and the imaginary components are both 0. So the real component is x prime prime plus x equal to 0, and the imaginary component is y prime prime plus y equal to 0, which means that the real and the imaginary components of the complexified solution are separately real solutions to the given problem. So we find that cosine and sine are solutions to y prime prime plus y equal to 0. And that is the technique of complexification. What you do is you take the given differential equation, complexify it, find the complex solution, and then, excuse me, the real and imaginary parts of the complex solution will be separately real solutions to the original problem. That doesn't actually do everything. You still have pesky things like y prime prime plus 2y equal to, plus y equal to 0. There you get a repeated auxiliary root to the auxiliary equation, lambda equals -1 twice. And then the other solution actually is stemming from generalized eigenvectors. All right, but anyway, more about that later perhaps. So anyway, just to complete this thought here, and I'll try to pick it up again when we meet again. Definition: if we have a linear transformation over the reals, and if v in the complexification of v is a non-zero vector, lambda, a complex number for which t sub c of v is lambda v. In other words, v is a complex eigenvector of the complexification of t. Okay? Then we say v is a complex eigenvector with eigenvalue lambda for t. Technically speaking, v is not an eigenvalue, or is not an eigenvector for t itself, because t has no eigenvectors. Possibly, I mean, lambda is not a real number, so this is not lambda is not an eigenvalue for t as a real vector space, as a real transformation on a real vector space. But it could be a genuine complex eigenvector with complex eigenvalue for the complexification of t. All right. So anyway, so if we have a complex eigenvector with eigenvalue lambda for t, that means that we have a complex eigenvector for the complexification of t. Furthermore, we can do the same for a matrix. If we have an n by n real matrix, and we get a non-zero complex vector such that AV is equal to lambda v, where lambda is some complex number, then we say v is a complex eigenvector with complex eigenvalue lambda of the real matrix A. And so in that sense, even though sometimes real matrices don't have, or real transformations don't have eigenvectors, or don't even have eigenvalues, that doesn't concern us much, because we can always take the real matrix or take the real transformation and form its complexification. And the complexification has a characteristic polynomial, which is over the complex numbers, which are thankfully algebraically complete, which means that the characteristic polynomial always splits. We always have n eigenvalues, possibly repeated in the complex case. And this, logically, is what lays the groundwork for what we call the real Jordan form. I showed you already an example of that. But I think I'll pick up here next time, because it kind of all goes together past here. And I hope I've shown you enough here to make you understand. I know this is kind of a little bit, you're probably tired of hearing me say complexification at this point. I think I've said it like 30 times in the last 10 minutes. So anyway, I'll see you guys Wednesday, I hope, and enjoy your weekend.